So this is going to be 5-4, the alpha lesson. Okay, and we're going to go over the, we're going to go through the Google slide. Okay. But just say, here's the question at the end. And this says, the area enclosed by the graph of this y equals and the x-axis. What's your option? Right? Technical question. Not complicated. Right? You see that question, what do you think of? What command on the calculator do you think of when you see that question? Math 9, exactly right. That's all there's to it. Math 9. Okay? All right, so here we go. This is the fundamental theorem of calculus. What's the fundamental theorem of algebra? Excuse me? Yeah, right? That the number of zeros corresponds to the degree of fault. That's the fundamental theorem of algebra. If something is 6 degrees, it has 6 zeros. How many are real? 6 or 4 or 2 or 9. Very good. How do you know that, man? Because last year you do it all the time. We count down. That's the fundamental theorem of algebra. This is the fundamental theorem of calculus. If you take the derivative of an integral, you get back to the parent. That might seem like common sense. Okay? But it's a little more involved. This is saying, take the derivative with respect to x of this thing here. So, right, we're doing this. We're working from right to left. Integrate this. Take the antiderivative of this, then take the derivative, and you're back to your story. Meaning what? This is that's the sum. This is the sum of all these rectangles, this high and that long. So that's the area of the graph. And if you take the derivative of that, you're back to the position. Or you're back to the, position. So, now look how they wrote this. This is saying, think of this. Think of f of x being the velocity. Then big F is the position. That's how they're telling you apart. So this is f of x. How are you getting that? You're anti-differentiating that, and then taking the derivative. So the derivative of big F, the derivative of big F, little. Yeah, ready? You have to look for this. Well, this is pretty straightforward. You have the derivative, the differential in front of the integral. Oh, you got to look for this. This is just like implicit differentiation. We have to see that the variables match. This letter has to match that letter. The lower limit has to be a constant. It doesn't have to be 0. It has to be any constant. Now think about this. When I say any constant, what is the derivative of any constant? 0. So this thing could be a 10. Could be a 0. Derivative of 0 is 0. It could be a 50. Derivative of 50 is 0. You're going to take the derivative. So you want the lower limit to be a constant. So what happened? This key is holding the place that x, you need what? You don't want to say this is x, the x, and take the f of x. Because that would just be confusing. What's f x am I talking about? The whole equation is dummy variables that called t. It's no form of the vernacular. So here's a question. Ready? Now this is in your book. This is example 1 on page 295. It is poorly written. We'll explain to you why. But here's the question. What do you want to do? You want to take the derivative of this integral. Yes, this one. So we work from right to left. Cosine is the derivative of sine. Remember doing the power rule reverse? It's a little confusing first doing. Now we're doing the derivatives of the straight functions in reverse. What's that? Because you can check your answer by backing up. This took care of that, the summation. That thing just came right there. So in order to do this work, what does that say? This is saying the sum of this height times that width will give you that. We're going to take the derivative of this, except what? See, this is why it's poorly written. Because they take the sine of negative pi. The sine of negative pi is here. And the sine would be 0. But let's change the question to negative pi over 2. So instead of this being a 0, it would be a negative 1. Yes. And negative times a negative will be a positive 1. So the derivative of sine x plus 1. Good? Would be cosine. It could be the same answer. So you could differentiate 1 and beta 0. And it was a beta example in the book because the sine of negative pi is 0. It doesn't have to be a 0. It just has to be a constant. See, the lower limit, as long as it gives you a constant value, when you take the derivative of it, it's going to give you a 0. And they shouldn't have picked a value. They gave you a 0 in the function. That was just wrong. Except what? You don't have to do that work. See, the point is, you can skip right to the answer. Why? Because you do have these large differentiating interval. These letters match. That's a constant. So all you're doing is pasting that there and saying, where did this come from? It came from the cosine. So, before we roll on to the next slide, tell me what the answer would be. Randy, say that out forever. Excellent. We're changing the variable. Makes sense? Because this is the variable we're going to use. That's all you're doing. What do you get to be your favorite thing in math? Look at you. What are you doing? You just follow the steps. All right. So far, so good. All right, well, this can't be what you said was challenging. Here we go. Okay. These don't match. What are we going to do? We're going to use the chain rule. What do you notice here? You did use the chain rule in the thought you just did. You just didn't notice it. Because when you did this, you multiply this thing by the derivative of the upper limit. The derivative of the upper limit was 1. But that's the identity of multiplication. You didn't notice it. No. So here, when it isn't a 1, we get this. Because the derivative of the upper limit is 2x, so I have to multiply my answer after you substitute, you plug it in, by 2x times the derivative of the upper limit. Make sense? Correct? I'm not changing the rules in the middle of the game. You did multiply by the derivative of the limit. The first 2 examples, they just have to be a 1. What is the matter with you, babe? If your nose runs and your feet smell, you're upside down. So the question's upside down. Yes? And this, you're used to seeing the upper limit, right? Reverse the limits. Now, this is a bigger deal than you realize. Reversing the limits. And we need to verify that with graphs. We're not there yet. But right now, we're just following the step. Properties of limits, that if we reverse the limits, we get the opposite answer. Okay? What would that take you to? Good. Done. Now what? We don't have a constant here, yes? So we're going to build. This problem is based on the last 2 examples, and we're combining what we did. We're going to break the question down into the sum of 2 integrals. We're going to go from 0 to upper limit x squared, and from the lower limit 2x to 0. So it's picking up here. Make sense? But it says it doesn't matter what constant it is. This doesn't have to be a 0. It could be a 5. It could be a 4. That's going to at least work for 5. So now what? We do these separately, except what this one is upside down. We make this subtract this, reverse the limits. Yes. Now we're going to use the chain rule. This x squared gets plugged into the t times its derivative. This 2x gets plugged into the t times its derivative. And you're there. Okay? So, part 2 is for the beta lesson. So here we're going to go to, ready? Example 2, let me bring it back up. In your textbook, example 2 was cosine t x squared is the upper limit. Okay, so I'm leaving that up there. That is example 2 in your book. That's your model. You to go to problem number 9, please. Or problem number 9. You see, we've got a 5, BC, and a 5 in statistics. His name's on the home page of Canvas. Say, well, here's how I did the problem. He enhanced it, so we gave a recognition on it. What have you got? You need 2x. You need to bring the upper limit. When you put the x squared in for t, you would get x to the 4th, so you end up with 2x e x power 4. Sorry. Now, example 4 is important, right? So we go to example 4. And it says this: find a function whose derivative is tangent when it goes through the point 3,5. So I build an H chart. You can see chart makes sense to me. That's the question. That's why it's important for you to build H chart. If you're at home, here's the H chart will do. The headings are x, y, and y prime. So the heading of the third column is tangent x. Then the values under x are 3, the values under y are 5. So what you're being asked for is what's the heading of the second column? Find the function whose derivative is tan x, and the parent rate goes from 3 columns. Now, all right, let's think back to the 3 derivatives. The derivative sign is derivative cosine is negative sign. The derivative of tangent is secant squared. Good? You keep going? Not likely. What do you count? Now that the ones that start with C are negative. Yes? Let's play Jeopardy. Tangent is the answer. What's the question? What derivative has it? What trig function has the derivative equal to tangent? There isn't one. Okay? So how are we going to do this? The way we write this is we set this up. And we say we want an anti-differentiating mean. We say y is the antiderivative, the sum of this height times that width from a lower limit that's a constant, the way they gave it to us, 3 to x. Well, what would happen? Ready? If we went from 3 to 3, tan t dt, what's that equal to? 0. Why? Because it has no weight. You good? We need it to be equal to 5. So we're going to just slide this graph up. We're going to make this an x. We're going to replace y with y, take away 5. We can slide the graph up. How come? Because this represents the area under here. The area under the derivative gives you a position. The area under the derivative gives you the position. That also works for this. The area under the acceleration gives you the velocity. The area of velocity gives you the position. You're going from right to left on the H stroke. So that's your model right here. You're going to problem number 25. Here's the question. The derivative is this. The derivative is this, and the parent graph goes to 0.7, -2. So we're going to anti-differentiate the derivative. The lower limit is going to be 7. It's given. So if we go from 7 to 7, we would get a 0. We don't want 7, 0. We want 7, -2. So to slide the graph down to, we replace y with y plus 2. Then what? Right? We're using the dummy variable here, t, dt, because we're going from right to left. What did you do earlier? You went from here. Take this thing and take a derivative of it, which gives you cosine squared x. Well, cosine squared 5x. That's given. Now you're going from right to left to get that. But again, we're combining some different things. We're using the H star, using the template to do a transformation to a slide. Okay? So that is it for the alpha lesson. It's a 2-day, 5 course, 2-day lesson.